Hello everyone, good morning, good afternoon, good evening, wherever you are in the world. Welcome to my session Beyond Keywords, Image Similarity Search in Azure CosmosDB for PostgreSQL. In the next 10 minutes, you will learn how to build vector similarity search on Azure CosmosDB for PostgreSQL using the pgvector extension and the Azure AI Vision multi-modal embeddings APIs. My name is Safidou and I'm a Microsoft MVP in Artificial Intelligence based in Greece. I'm interested in cloud technologies, Azure AI and IoT, and I maintain a technical blog where I post articles about technologies I'm passionate about. If you have any questions, feel free to reach out to me on LinkedIn. So before exploring what vector search is, let's understand the problem that we are trying to solve. Unlike traditional search systems that rely on mention of keywords, tags, or other metadata to retrieve similar images, vector search systems leverage machine learning to capture the meaning of the data. This approach enables users to search based on the intended meaning rather than exact matches on keywords. For example, if you remember the key aspects of the movie, you can retrieve the desired film by describing the scenario without even using the exact keywords found in the original description. So in this session, you will understand what vector embeddings is, and you will explore how a vector search system works. You will also build a similarity search application using Azure CosmosDB for PostgreSQL and the Azure AI Vision multi-modal embeddings APIs. So vector search is based on the conversion of unstructured data such as text, images, audio and video into a numerical representation which is called a vector embedding. You can think of a vector embedding as an array containing numerical values. These arrays are high-dimensional and dense and summarize the information contained in the original data. Vector embeddings can be generated using machine learning models that are capable of capturing the meaning of the original data, identifying patterns, and identifying similarities between the data. But what is so special about vector embeddings that makes them so useful? By converting unstructured data into a numerical representation, we can measure the similarity of the original data by calculating the distance of the corresponding embeddings. For example, by visualizing the word embeddings into the two-dimensional vector space, we can see that the words cat and kitten, which are semantically similar, are located close together, while the words car and bus, which are dissimilar, are placed further apart. To calculate similarity, you can use standard distance metrics such as Euclidean distance or similarity metrics such as the cosine similarity. Cosine similarity is actually one of the most widely used similarity metrics in a vector search system. Vector search system works by comparing the vector embedding of a user query with a set of predefined vector embeddings to find a list of vector embeddings that are most similar to the query vector. Vector embeddings are typically stored in vector databases, which are specialized type of database optimized for storing and querying vectors with a large number of dimensions. In this vector search system, it is essential to use the same embedding model for calculating the vector embeddings of an object. In Azure CosmosDB for PostgreSQL, vector similarity search is enabled by the pgvector extension. To use this extension, you should first create it using the select create extension command. The pgvector extension introduces a new data type, vector, which we can use when creating a table to indicate that the column will contain vector data. For example, consider that we want to build a table for an art gallery. This table will contain information for each painting, like its style, artist name, a short description, a link to the original image file, and a vector embedding generated from the image file. You can also specify the number of dimensions of the vectors, which in our case is equal to 1024. To retrieve similar paintings, you can use SQL select statements and the built-in vector operators. For example, the select statement calculates the cosine distance between the query vector and every vector stored in our database, sorts the result by the calculated distance, and then retrieve the 5 most similar images. Let's see a short demo. For example, we want to find paintings that depict a table with flowers. First, we calculate the vector embedding of our query using the vectorized text API, and then we use the query vector in our SQL select statement. As you can see, we have retrieved paintings depicting a table with flowers without using any other type of metadata. You can also search for paintings using another painting as a reference. For example, in this we will use the Still Life with Flowers painting as a reference. And first we calculate the vector embedding of our query using the vectorized image API, and then execute a SQL select statement to retrieve the similar paintings. And again, we have successfully retrieved paintings that are similar to our reference painting without using any other type of metadata. This type of search is called exact nearest neighbor search because it compares the query vector with every vector stored in the database. And while this type of search provides the perfect record, it can lead to larger search times. So to enhance efficiency when using larger datasets, we can create indexes to enable approximate nearest neighbor search, which trade-offs result quality for speed. pgvector supports two types of approximate indexes, the inverted file flat or IVFFlat index and the hierarchical navigable smart word or XNSW index. The IVFFlat index works by grouping the vector embeddings into clusters, also known as Voronoi regions or cells, and limiting the search scope only to the few nearest clusters for each query instead of the entire dataset. The XNSW index is based on the construction of multi-layer proximity graphs. It's one of the most popular and best-performing algorithms for approximate nearest neighbor cells, and is also available in the majority of the vector databases. To create an IVFFlat index, you can use the create index statement and specify two parameters, the distance metric that you want to use when creating the clusters, for example the cosine distance, and the number of clusters that you want to create, for example 15. It's essential to create the IVFFlat index once the table is populated with data, and if you add more vector embeddings in your table, you should repeat the index in order to calculate the new cluster centroids. An XNSW can be created using the same command, and in this case we should specify two parameters that are related to the construction of the multi-layered graph. Since the XNSW algorithm is pretty complex, I highly recommend reading the relevant research paper in order to understand how these parameters affect the performance of the XNSW index. Let's see a short demo. Again, we are trying to find paintings that depict a table with flowers. We follow the same steps to calculate the query vector and execute the same SQL select statement. As you can see, we are able to retrieve the same paintings obtained using exact nearest neighbor search, but with a lower search time. To view the execution plan, you can prefix the SQL select statement with the explain analyze keywords. If you are interested in this topic, you can check out my project on my GitHub repository, and you can also find some useful information on Microsoft Docs. Thank you and enjoy the rest day at Python Data Science Day.